So how do we calculate the probability of mutually exclusive events, or the probability of not mutually exclusive events? And more importantly, what's the difference between the two of them here? We care about whether our events are mutually exclusive or not when we are dealing with compound events, so two or more events considered at the same time, and we've asked a question that involves the probability of one or the other occurring. Okay? So if A and B are not mutually exclusive, then the probability of A or B, and another way of writing probability of A or B is A union B, is going to be equal to the probability of A plus the probability of B minus the probability of A and B. So this is basically our principle of inclusion and exclusion that we've seen before. That we have the number of events in one set, the number of events in the other set, and we have to subtract off the events that are in both so we don't count them twice. Okay? If A and B are mutually exclusive, then we know that the probability of A and B, okay, or the probability of the intersection of A and B, to write it another way, we know that that's going to be 0. Okay, because these events are mutually exclusive. They can't both occur at the same time. There's no elements that are in both of the sets. So the probability of A or B, or the probability of A union B, for mutually exclusive sets is just the probability of A plus the probability of B. Okay? Somewhat simpler. So let's take a look at an example. We got two examples here that are similar. A card is randomly selected from a shuffled deck of cards. What is the probability that either a heart or a black face card is selected? So first off, they're asking us an or question here. So we care about whether these events are exclusive, mutually exclusive, or not mutually exclusive. Are these two events mutually exclusive? Well, let's figure out what events we are interested in here. Okay? Let's let event A be the event where we pick a heart. And we'll let event B be the event where we pick a black face card. Okay. Now remember, a black face card, by face card they mean Jack, Queen, or King. The ones that actually have faces on them. And we're assuming they're no jokers. I guess the joker would have the face on it as well. So these are our two events, A and B. Are A and B mutually exclusive events? What do we think? Yes or no? They're not mutually exclusive? Or yes, they are mutually exclusive? Why not? Yeah. So you can't have both of these at the same time, so they are mutually exclusive. Okay? So let's write this down here. I'll just put this over at the side. Mutually exclusive. Okay. So our probability, this thing that we're trying to find, is going to be the probability of A or B, A union B, is going to be the probability of A plus the probability of B and that's that. Okay. So if we're picking one card from this shuffled deck here, we know that in all of these cases, the number of things in our sample space is going to be 52. There are 52 possible cards that we can draw here. So to calculate our probabilities, we want, for our probability of A, we want the number of ways that we can pick a heart out of these 52. Well, there are 13 hearts in our deck, so 13 over 52. What is the probability of getting a black face card? Well, there are 3 black face cards that are clubs, 3 black face cards that are spades, so there are 6 black face cards in total, so 6 out of 52. So our total probability that we're interested in here is going to be 19 over 52. Now let's think about example 2 here. A card is randomly selected from a shuffled deck of cards. What is the probability that either a diamond or a red number card is selected? Again, they're asking us an OR question here, so we care about whether these events are mutually exclusive or not. Are these events mutually exclusive, or are they not mutually exclusive? What do we think? Why? They are not mutually exclusive because it's possible that the red number card that we get could also be a diamond. Okay? So we could draw a card that is a diamond, we could draw a card that is a red number card, or we could draw one that is both. Okay? So picking a diamond doesn't exclude the possibility that we're also going to have a red number card, and vice versa. If we pick a red number card, it doesn't exclude the possibility that we also have a diamond. So if these are, so let's again define our sets here. We'll say let A be the event where we pick a diamond. We'll let B be the event where we pick a red number card. And our number cards go from 2 up to 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. We won't count ace in there because it's like a letter card. I don't know. It's its own category or something like that. So our probability that we're interested in is we want the probability of A or B. So A union B is going to be probability of A plus the probability of B minus the probability of A and B. Okay? So we want to take out those ones that are included in both sets. Otherwise, we end up counting them twice when we do our probability. So our probability of A is probability of picking a diamond. So we have 13 diamonds out of our 52 cards. Okay. Probability of B is a red number card. So let's see, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 9 of them, and there are 2 red suits. So that's going to be 18 out of 52, including both the hearts and the diamonds. What kind of cards are included in this intersection of A and B? Well, they are all of the diamonds that are also number cards. So how many of those are there? Well, there is 2, 3, 4, 5, 6, 7, 8, 9, 10. So 9 out of 52 to express it as a probability. Okay, so our probability of picking a number card that is also a diamond is 9 out of 52. So we do this subtraction and we get our probability is 22 over 52, which I should simplify here to 11 over 26.